everyone. I've gotten a couple questions about the second question on Tuesday's quick check. So if you got stuck on that one as well, or if you figured out the answer but you're really not sure why it works, I'll be glad to give you a slightly more detailed walkthrough because it is a bit of an extension of what we've been doing and it's a more challenging USUB. And while I certainly hope that you've at least tried it and not just kind of settled for the answer, I don't want you to be completely stuck. So hopefully this will help. The first thing that you should probably do is set up the USUB itself, which by now should be relatively obvious as x plus 1, since that's the inside of our chain rule. So in my side work, I'll set up u equal x plus 1, and then in my actual workspace, so as usual, I'll just kind of separate it there, I'll start with my initial substitution. Now I'm not going to write any limits because I know I'm going to end up changing those. And I have x over square root of u dx. Now, if you kind of thought a couple of steps ahead, you probably noticed that moving the x to the dx and kind of linking them together doesn't really end up helping, because when you do your derivative, du equals, you actually don't end up with x dx, which almost always seemed to happen up to this point. But when you do your derivative, you just get dx. So it almost seems as though you have a trivial substitution. Now you're at the point where you have the integral of x over square root u du, but you're still stuck with that x on top. And this is where I think people got stuck, because we've never had this situation before where one of the variables just doesn't work out. But just so you can kind of see an alternative strategy here, if it wouldn't have occurred to you you can do this, here's actually something that you are algebraically allowed to do. Remember, all you're able to do is substitutions. So even though that might sound like you have limited options, sometimes we don't really think about all the possible substitutions we can make from our side work. We're usually focused on substituting the letter u and the letter dx, but nothing really else ever seems like it's ever been eligible for substitution. And I just want to point out to you that if the value in question is an x, if that's the part that I'm currently worried about, I do have an x in my side work that I can work with. So let's consider, if we can, using our side work slightly differently than usual. If I got the x by itself, then I would have u minus 1 equal to that x, which again doesn't really seem like it's very interesting, but that is at least in terms of u, and I wanted this problem in terms of u. So if I make another substitution, I'll replace the letter x with u minus 1 over square root u du, and while that might not seem like that's a doable problem, this is actually completely doable. This is an integral we can do. If you're not sure how, because to you it still looks like a quotient rule, consider a couple of quick rewrites. On the bottom, square root of u is u to the 1/2, which is basically just a power function. Now, anytime you have a single term on the bottom, you can actually split the fraction into two pieces. So I can split this into u over u to the 1/2 minus 1 over u to the 1/2 du. We're totally allowed to do that because as long as there's a single term on the bottom, that split is mathematically allowable with the rules of fractions. If there was a minus sign or a plus sign on the bottom, then we couldn't. We'd have to use something fancier called partial fraction decomposition, which nobody wants to do. So this little split is completely mathematically okay. I'll put parentheses just for formality, but at this point, let's just think about this. U is technically u to the power of 1. And if I think about how fractions work, exponents in fractions can subtract to simplify. So u minus 1/2 really just simplifies to u to the 1/2. 1 minus 1/2 is 1/2. Then minus, this interesting little fraction can just be a negative exponent usage, u to the negative 1/2. And now I have two power rules. This is actually a totally doable antiderivative. The only thing that we still have to do, and I'm going to go back to my side workspace for a second, is I have to convert my coordinates. Remember, x coordinates were originally 0 and 15, and I need to convert those to their corresponding u coordinates. So if x is 0, u is 0 plus 1, which is 1. If x is 15, u is 15 plus 1, which is 16. So now I can actually finish the problem with the values of 1 and 16. So I'm not going to finish the problem for you on the video. I'll kind of leave that as an exercise for you. But at this point, it's just a power rule. Do your traditional power rule for u to the 1/2. Get your antiderivative there. Do your traditional power rule for u to the negative 1/2. Get your antiderivative there. And then evaluate your antiderivatives at 16 and 1. Do your subtraction, and it should end up being a surprisingly nice integer value. Weirdly enough, although it probably didn't seem like it, this answer does have an integer value. So if you get stuck from here, feel free to send me an email and follow up. But hopefully this gives you an idea of some out-of-the-box algebra that you can try for an example that does ultimately work out really nicely, just might have looked different enough that if you got thrown off, you might have thought, oh, this one's impossible. Remember, no integral problem, specifically no u sub problem, is impossible. You just have to try to think creatively about different substitutions you can make in order to rewrite the problem into something that ultimately is a power rule or recognizable derivative.